Hey there. So, let's dive into a pretty comprehensive recap that covers all the key points from that study guide session, focusing on geology, geologic time, and oceanography. This should give you a solid understanding without having to slog through the entire transcript yourself. First off, we explored foundational ideas about how Earth's surface changes over time. There's this big contrast between two major concepts: catastrophism and uniformitarianism. Catastrophism is the idea that the Earth's features change mostly through sudden, dramatic events. Think massive floods or earthquakes that reshape landscapes all at once. Historically, people used this to try to square geological evidence with a relatively young age of Earth, like 6,000 years. On the flip side, uniformitarianism, summed up as the present is the key to the past, means the same natural processes we observe today, like erosion, sedimentation, and volcanism, have been operating consistently over Earth's history. So, the slow, steady changes we see now explain how landscapes evolved over millions or billions of years. Moving into geologic dating, it's crucial to distinguish between relative and numerical dating. Relative dating is about sequencing events without assigning specific ages, like saying one rock layer is older than another based on position. Numerical dating, on the other hand, tries to pin down a more exact age in years, often through techniques like radioisotope dating. To help make sense of sedimentary rock layers, there are 4 key geologic laws you should know. The law of superposition is the big one. In undisturbed sedimentary layers, the bottom ones are older, and the layers on top are progressively younger. Then there's original horizontality, which tells us sediment layers form horizontally, so if they're tilted or folded, something disturbed them later. Cross-cutting relationships explain that if an igneous intrusion or fault cuts through layers, it's younger than those layers. Finally, lateral continuity says that layers extend horizontally in all directions until they thin out or meet a barrier, even if they're eroded in some parts. That leads nicely into unconformities, which are basically gaps in the geologic record. These form when layers are eroded away or no deposition happened for a while. There are 3 main types. Disconformities, where sedimentary layers are parallel but have a time gap between them. Angular unconformities, where older layers are tilted or folded before newer layers sit atop them. And nonconformities, which involve sedimentary rock resting on much older igneous or metamorphic rocks. Switching gears a bit to fossils and paleontology. The study of fossils, we learn a lot about Earth's past life and environments from fossil records. Fossils form when organic materials get replaced by minerals over time, preserving shapes or traces like footprints or burrows. These fossils help us correlate rock layers and understand their relative ages. For example, index fossils like trilobites lived during specific time ranges and can tell us the age of the rocks they're found in. Radioisotope dating builds on this concept by using the known decay rates of unstable isotopes to date rocks numerically. The concept of half-life is essential. It's the time it takes for half of a radioactive parent isotope to decay into a stable daughter isotope. Uranium-238, for instance, decays into lead-236 over about 4.5 billion years, helping date some of Earth's oldest rocks. Carbon-14 dating works similarly but is for much younger, organic material and is based on how long it takes for half of the C14 isotopes to decay after an organism dies. 1 complexity. Numerical dating works well with igneous rocks, since their formation date corresponds directly with the rock cooling. But for sedimentary rocks, since they're made of fragments from older rocks, dating those fragments tells you their age but not when the sedimentary rock itself formed. That's why relative dating and fossils are often better for sedimentary layers. Taking a step back to the grand scheme, the geologic time scale organizes Earth's history into eons, eras, periods, and so on. Keep in mind the broad strokes. The Precambrian is older than the Phanerozoic. Within the Phanerozoic, you'll find 3 major eras: the Paleozoic, Mesozoic, and Cenozoic. Dinosaurs lived during the Mesozoic, which ended about 65 million years ago when they went extinct, likely due to asteroid impact and volcanic activity. Mammals became dominant during the Cenozoic, and the Paleozoic was the era where complex marine life exploded, including the famous Cambrian explosion. Coming to Earth's habitability, several conditions make it possible for life as we know it. Distance from the sun allows liquid water to exist not too hot or cold. Oxygen in the atmosphere is vital, and that increased dramatically around 2.5 billion years ago during the Great Oxidation Event, thanks to early photosynthetic bacteria. Another key factor is Earth's magnetic field, generated by the molten iron-nickel core acting like a giant bar magnet. This magnetic shield protects us from harmful solar winds and cosmic radiation, and helps Earth retain its atmosphere, something Mars lost after its magnetic field disappeared. Zooming out further into the universe, the Big Bang produced mainly hydrogen and helium. Stars fuse these elements into heavier ones like carbon and iron. When massive stars explode in supernovae, they scatter these heavier elements across space, enriching clouds of dust and gas. These clouds eventually collapse under gravity, forming new stars and planets. Our solar system, according to nebular theory, formed from such a spinning disk of gas and dust. The early Earth was incredibly hot, primarily due to ongoing collisions with other bodies and the heat from radioactive decay inside the planet. As the Earth cooled, heavier elements like iron and nickel sank to create the core, while lighter materials rose to form the crust and mantle. Early volcanic outgassing released gases that formed Earth's initial atmosphere and contributed water vapor. Once the planet cooled enough, water vapor condensed to form the oceans. Plate tectonics have evolved with Earth's cooling. Back then, hotter mantle temperatures meant less subduction and more sluggish or different plate movements. Over time, continents formed by accumulating small crustal fragments. The supercontinent cycles, with landmasses repeatedly assembling and breaking apart, strongly influence climate and sea level. For example, during times of fast seafloor spreading, more buoyant material pushes ocean water inland, raising sea levels, as seen in the Mesozoic when North America had large inland seas. The separation of Antarctica from South America changed wind patterns and led to modern Antarctic ice sheets. Speaking of continents, the Appalachian Mountains formed from collisions related to the rifting of the supercontinent called Pangaea, linking them to mountain ranges in Europe and Africa. The Sierra Nevada and Rocky Mountains owe their origins to mountain building during the Mesozoic along the western U.S. Life's beginnings on Earth remain partly speculative but with strong models. Life likely originated in the oceans, possibly around deep-sea hydrothermal vents called black smokers, where chemical energy and nutrients abound without sunlight. Another model suggests early amino acids and proteins formed in Earth's early atmosphere, sparked by electrical discharges, a concept famously demonstrated in the Miller-Urey experiments. Recognizing the difference between prokaryotes and eukaryotes is key. Prokaryotes, like bacteria, are simple single-celled organisms without a nucleus, while eukaryotes have complex cells with nuclei and organelles. Life diversified from these beginnings, with the Paleozoic dominated by marine life and early fish, the Mesozoic known as the age of reptiles and dinosaurs, and the Cenozoic as the age of mammals. Plant evolution paralleled this. Early plant life depended on water but gradually moved inland with the development of seed plants. Gymnosperms were dominant during the Mesozoic, producing seeds but no flowers, while angiosperms, the flowering plants, proliferated in the Cenozoic, enabling ecosystems like grasslands and supporting new herbivore communities. Shifting focus to oceanography, about 70% of Earth's surface is covered by ocean. The largest oceans are the Pacific, Atlantic, Indian, and Arctic. Understanding the ocean floor's topography bathymetry came much later thanks to sonar mapping, which measures the depth by timing sound waves bouncing off the ocean floor. The ocean floor is divided into several major features. The continental shelf, the underwater extension of continents, continental slope, where the seafloor drops off steeply, and the abyssal plains or ocean basins. Sometimes we find deep canyons and oceanic trenches, especially near active continental margins. Continental margins come in two types: passive and active. Passive margins, like the Atlantic coasts, aren't near tectonic boundaries and have little seismic activity. Active margins, like the Pacific coast, coincide with plate boundaries where subduction causes trenches, earthquakes, and volcanoes. Mid-ocean ridges are underwater mountain ranges created at divergent plate boundaries. Here, tectonic plates pull apart, new ocean crust forms from magma, and we get features like transform faults fractures that offset sections of the ridge. One cool thing to remember: the youngest oceanic crust is always found near these mid-ocean ridges, where new crust forms. The oldest crust tends to be closer to the continents, where it can accumulate thick layers of sediment over time, since it's been sitting there much longer. Speaking of sediments, the ocean floor collects various types. Biogenous sediments from once-living organisms, like shell fragments made of calcium carbonate. Hydrogenous sediments formed by chemical precipitation, like from hydrothermal vents. Lithogenous sediments eroded from land, and cosmogenous dust from outer space. These sediments not only cover the seafloor, but can also record climate history. For example, oxygen isotopes in fossilized shells vary with temperature, letting scientists infer past ocean temperatures and climate changes. Salinity, or the salt content of seawater, is influenced by several processes. Salts mainly come from weathered rocks on land, delivered by rivers. Evaporation increases salinity by removing water, while precipitation, melting ice, and freshwater runoff dilute salt. Salinity tends to be highest in mid-latitudes, where evaporation is strong but precipitation is low, lower at the equator due to heavy rainfall, and also low near the poles due to melting ice. Temperature affects salinity and density, with warmer water being less dense. At the equator, surface water is warmer because the sun's rays hit directly, whereas at poles the sunlight is spread thinly. Water density and temperature usually decrease with ocean depth, creating a thermocline where the temperature drops rapidly with depth, though this varies by latitude. When talking about ocean life, it's helpful to divide organisms into categories based on habitat and behavior. Plankton drift with currents. Phytoplankton, tiny photosynthetic algae, and zooplankton, tiny animals. Nekton are free swimmers like fish and whales. Benthic organisms live on the ocean floor, ranging from corals to bottom-dwelling worms. Most ocean life concentrates near the surface because sunlight is essential for photosynthesis. This light penetration defines oceanic zones and strongly influences food webs. Productivity. The rate of photosynthesis and biomass generation varies regionally and seasonally. Equatorial waters, though warm and light-filled, often have lower productivity because strong thermal stratification limits nutrient mixing from deeper waters. Mid-latitude regions can experience seasonal blooms when nutrients mix upward in spring. Understanding ocean food webs is crucial. A food chain is a simple linear path of who eats whom, while a food web is a complex network where species have multiple food sources and predators. So, by wrapping all this up, this study session covered a wide range of geology and oceanography fundamentals. From how we date rocks and interpret geologic history, to Earth's formation, plate tectonics, and habitability, to fossil evidence of life's evolution, and finally the structure and processes of our ocean and its ecosystems. All these pieces connect together in the story of the Earth, its dynamic surface, its past climates, and its diverse life, both above ground and beneath the waves. Hopefully, this guided tour helps you grasp the highlights and essential concepts without having to wade through a ton of detailed notes. Remember, focusing on the big ideas and how they interrelate makes it way easier to understand Earth's complex history and systems. Thanks for sticking with me through this deep dive. Catch you next time for more explorations of our amazing planet.